a little bit. But before I start, I would like to thank my collaborators who helped me on these projects. Nick from our OGS director, Jake from OGS seismic team, Russell from OGS GIS team, Anna Turnini and Matt Prenters from School of Geoscience, University of Oklahoma. So I guess we all here should be aware of the problems we are facing right now, where the CO2 concentration in the atmosphere is increasing due to our use of fossil fuels. And most of us are also probably know some of the solution to that. For example, switching the fuels, using more methane gas or natural gas, and probably using more renewable energies. So today I'm going to talk another approach, what we call as geological carbon sequestrations, which is one of the key elements in carbon capture, utilization, and storage. And the overview of this talk is like this. I'm going to summarize the crisis of the climate change or climate crisis, and then looking at the sources in United States and also Oklahoma. And then I will focus most of the time on the geologic carbon storage, especially in Oklahoma. And then I will talk a little bit about OGS role and what we do in terms of the research in the Oklahoma Geological Surveys related to these carbon management projects. So the problem can be illustrated by, in a nutshell, by these figures. So let's say we have carbon emissions from fossil fuels combustions, and they produce a lot of carbon in terms of in the forms of CO2, and it is released to the atmosphere more than what this biosphere's carbon storage, the terrestrial ecosystem on the continent, as well as the ocean can absorb over the time scale we are emitting it. So basically, it is building up in the atmosphere. And as it goes, it causes global warming, it causes climate change. So what I'm going to talk about, again, will be the sources of this CO2, as well as the potential carbon sinks in Oklahoma. So before we go there, let's see what is the CO2 emissions in United States. This is the United States greenhouse gas emission by gas from 1990 to 2020, with the year in the x-axis and the emission million metric tons of carbon dioxide equivalents in this y-axis. Of course, there is a lot of information here, but I would like to point out two things here. You can see here in 2007 up to now, we see the trend is going down. It's like going down from 7.5 gigaton greenhouse emissions down to about 6 gigaton in 2020. That's a good sign, of course. And out of those 6 gigaton greenhouse gas emitted in 2020, 80% of that is the carbon dioxide. So that means we are emitting for about 4.8 gigaton CO2 in 2020 itself. And then the second one is what is or where are the CO2 come from? As you can see in this pie chart, mainly those about 4.8 gigatons CO2 is coming from transportation, electric power, industry, residential and commercial, and other non-fossil fuels combustion, like for example, wood, biomethanol, bioalcohol, biodiesel, something like that. And this 4.8 gigaton is the primary source available to be captured in United States. So let's go into a detail specifically for the CO2 emissions in Oklahoma. So in 2019, Oklahoma energy-related CO2 emission is estimated about 91 million metric tons. It ranks 23 in the country, and that is including the recorded and unrecorded or unreported CO2 emissions. And the total reported emissions from 151 facilities in Oklahoma contribute about 47 million metric tons of CO2. And this map shows the location of those 151 facilities, color-coded with the sectors, including the power plant, petroleum and natural gas processing plants, landfill, iron mills, chemicals plants, and etc. And then this the symbol size, the circle size here represent a relative value. So that means the bigger the circle, meaning the bigger the CO2 emissions. And then on the right side here, on the right side down here, we can conclude that power plant, chemical, and refinery are the top 3 biggest contributor in terms of the CO2 emissions in Oklahoma. And then we all know that carbon capture, utilization, and storage is an expensive process. And to motivate the CO2 deployment, the federal government has provided incentive as the 45Q tax credit. So I want to know what will be the available CO2 emission in Oklahoma that are qualified for those 45Q tax credit. On this left side, we have the key element of the section 45Q credits. Just forget about this one on the old deal, because we have reached about 93% quota, meaning about 75 million tons of CO2 has been captured and sequestrated. So it's almost done deal. And just focus on this right section where it is a new agreement for any equipment placed in service on February 2018 and later. So to be qualified for the 45Q tax credit, any power plants must capture at least 500,000 metric tons of CO2. And any facility that emit no more than 500,000 metric tons of CO2 per year must capture 25,000 metric tons of CO2. And then any direct air capture or other capture facility must capture at least 100,000 metric tons of CO2. So that means on top of those 151 facilities, only 23 facilities are qualified for this tax credit, because only 23 facilities fall into this annual capture requirement. And that is represented by these 4 main sectors: power plant, chemical plants, refinery plants, and pulp and paper mills. And those 4 sectors provide at least about 36 million tons of CO2 equivalent to be captured and stored in Oklahoma. So before we go to the geologic carbon storage, I would like to briefly discuss about 2 things: the CO2 phase diagram and also the CO2 trapping mechanisms. As we can see here, this is a generalized CO2 phase diagram with temperature on the x-axis and pressure in the y-axis. We got a solid CO2 phase where the temperature is lower. We typically know this as dry ice. And we also have the gaseous CO2 phase, what we have here as in the atmospheric conditions. And we have this liquid CO2 phase, which is the ideal phase for CO2 transportation via the pipeline. And pay attention on this supercritical CO2, which is the ideal phase for geological storage. The supercritical fluid regime is referred to CO2 phase where they are kind of like fluid or liquid in terms of the density, but also kind of like gas in terms of the viscosity. So this can be reached at the temperature greater than 31 degrees Celsius and the pressure more than 7.4 megapascal, which is the temperature and pressure condition at the depth of 2,500 feet below the surface. And then I would like to talk in general about the CO2 trapping mechanisms. As you can see here on this upper left, this is the % contribution of trapping for these 4 trapping mechanisms, including the structural and stratigraphic trappings, residual CO2 trappings, solubility trapping, and mineral trappings. I'm going to discuss or explain briefly about this trapping, but pay attention on this time since injection stop. So once the injection process of CO2 stop, notice that the % contribution of this structural and stratigraphic trapping is actually diminished at the expense of this residual solubility and mineral trapping increase. And then let's go to this structural trapping and stratigraphic trapping. So this is what happened in this structural and stratigraphic trapping mechanism. It happens when a buoyant fluid travel through permeable rocks until it cannot go further anymore, being trapped by a cap rock or impermeable layers. So this is, we know this is the mechanism where we have the oil and gas trapping mechanisms. And then the residual CO2 trapping mechanism, for me, this is the most interesting, the most compelling mechanism. As you can see here, this is let's say this is a pore space in a rock. And then this narrow area is the pore throat. And then this big bulb is the pore body. Assume that initially the pore space is filled by brine water. So when we start to inject the CO2 will flow into the pore throat and pore space as a drainage process, meaning that it will replace the initial fluid, which is in this case is the water, as a non-wetting phase. So in this case, the CO2 is a non-wetting phase, and this water is a wetting phase. And continue injecting the CO2 will fill all of this pore space, leaving only a rim of brine water because the water is a wetting phase. So they have a tendency to stuck to the rock. And then continue injecting the CO2, and then when we stop, the CO2 will keep moving in this pore space probably due to buoyancy forces or probably due to regional pressure gradient. And when that happened, since the brine is a wetting phase, it has a tendency to flow back to the pore. And when that happens, it's kind of isolating this CO2 as a residual. So this is how the residual CO2 trapping mechanism works. And then solubility trapping, of course, this is a pretty straightforward process. We all know about carbonated drinks, and we probably have tasted. We know that CO2 will dissolve in water. So that is basically what happened here. We dissolve the CO2 in water. The neat things about the solubility trapping is like when we inject the CO2 into the water will become denser compared to the water without CO2. So they have a tendency to move or flow downward, which is a good thing in these trapping mechanisms. And then the last one is the mineral trappings. This is a complicated process, and I'm not going to explain it in detail, but many research have shown that when we have a primary mineral, for example, quartz, kaolinite, calcite, elite, oligoclase, feldspar, exposed to CO2, the CO2 with the water will dissolve a little bit of them and release the cation. And then those cations, when subject to CO2 molecule, they will form secondary carbonate mineral, for example, like this magnesite, siderite, ankerite, and dawsonite, which is considered the most stable carbonate form of trapping CO2. So let's conclude or summarize the CO2 properties and CO2 trapping mechanisms. And now let's talk about the carbon capture, utilization, and storage. These typically refer to the process of capturing the CO2 from large stationary sources like the power plant, and then either reuse it as a EOR or in biological or chemical transformation to make plastic or synthetic fuels or etc. Or store it in a deep subsurface formation as a geologic sequestration. Now, let's see what is the geological storage option we have. This figure is from the IPCC report, and it shows the cross-section of a sedimentary basins with a depth of 1 kilometer and 2 kilometers. Note that most of the reservoir here is deeper than 800 meters. We remember that line, that 800 meter is the dividing line between either liquid and gas phase with the supercritical phases. So we need to inject that CO2 into any reservoir that is deeper than 800 meter depth, except these coal bed methanes, because there is a different mechanism happens here. The CO2 in this coal bed methanes is absorbed, so there is no requirement for the depth to make this works. So now let's talk about the geological carbon storage potential in Oklahoma. We published this map as a fact sheet back in 2011. This basically shows Oklahoma with all of those geological carbon storage potential. I know it looks like it's a little bit crowded because of the color is superimposed. So let me walk you through it. This yellow light yellow area represent the saline deep reservoir or formation, as well as the organic rich shale potential area for the CO2 sequestration. And this yellow area represents the unmineable coal, as well as the coal bed methane field as a potential source for CO2 sequestrations. And this light pink, it should be bigger than this, covering this Wichita uplift as well as this Arbuckle uplift represents the Basalt reservoir as a potential storage for CO2. And this green and red shaded area represents only some of the depleted oil and gas reservoir. Note that this blue area, which is the active CO2 EOR projects in this in the Burbank field of Osage Nations. So let's go into a detail for this all potential we have in Oklahoma. The first one is the deep saline aquifers. And to have this to work, the deep saline aquifers must have a depth deeper than 2,500 feet or 8,800 meters. And the total dissolved solid must be greater than 10,000 ppm. And in Oklahoma, this Arbuckle group is the one that is suitable fall into this category. As we can see in this cross section from A to B and C to C, we can see that we have a pretty thick Arbuckle groups below 2,500 feet, and it's covered by a regional cap rock, which is this Sylvan Shale, as well as the Woodford Shale on top of this. It's not shown here. And excuse me. And then this structural map, depth structural map in Oklahoma show that most of this area to the left of this orange shaded area is suitable for CO2 sequestration in for this Arbuckle group because they are deeper than 2,500 feet. And this isopac map showing that the Arbuckle has a thickness between 500 feet in the north and the east of Oklahoma, down to about 5,000 feet in these Anadarko basins. And the TDS map show that most of the area in the Oklahoma is well suited for carbon storage because they have more than 10,000 ppm TDS. So the second one is the oil and gas field in Oklahoma. So oil and gas field in Oklahoma is very unique because we know that they have a great or geologic characteristic that make them excellent for carbon storage. They have a proven record to hold hydrocarbon in geologic times. So in Oklahoma, we have about 3,200 big and small oil and gas field, including 1,800 oil field, 900 gas field, and then about 400 mixed oil and gas field. And the neat things about this oil and gas field in Oklahoma is like, we have a lot of data, informations, and knowledge about the subsurface that can support us to estimate and calculate the CO2 effective storage capacity using these equations. So the unmineable coal beds, by definitions, the unmineable coal bed is any coal bed that is too thick or too thin to be mined with current technology. So to have it works, the depth must range between 600 meters to 1,000 meters. Because any depth more than 1,000 meters the permeability will reduce significantly. And then why coal beds then? The coal has a large internal surface area. So to give you a perspective, 1 gram of coal can contain as much surface area as several football field. So therefore, they provide a large area to absorb large amount of CO2. Beside that, the CO2 is more absorbing than methane, thereby giving it the potential to effectively replace the methanes while absorbing the CO2 on the coal surface. And also the coal bed can play dual roles. They can be a source of methane and also a repository for the carbon storage. So in Oklahoma, we have this coal bed methane field in the Arkoma basins and Cherokee platform, mainly in the west Oklahoma, and we have like tens of coal beds in this area, and those coal beds has a thickness ranging from less than 1 foot up to several feet. The next one is the unconventional organic rich shale. This organic rich shale has behavior very similar to the coal. They tend to desorb methane and absorb CO2. And in order to make this organic rich shale work for CO2 sequestrations, the organic shales must be having a depth more than 2,500 feet, and the TOC must be greater than 2 weight%. It must be methane bearing, and it must be has been or will be stimulated for carbon production before or during the carbon storage process. And then why organic rich shales? Similar to the oil and gas, it has a high certainty in the integrity in terms of CO2 storing, because they have a proven record to hold the gas in place for millions of years. And then they have a well-established fracture networks thanks to the horizontal drilling and compression technology. And also, when we inject CO2 to the organic rich shales, they tend to enhance the production of methane. So in Oklahoma, the Woodford shales is actually fall into this category. It has TOC up to 28%, and based on this TOC present day map generated using around 3,000 cutting samples from about 400 wells, we can see many area in Oklahoma fall into this category, which is more than 2% with 2% TOC. And then the depth structure also show that many of the Woodford shales is deeper than 2,500 feet. And this vitrinite isoreflectance map of Woodford shale, we can filter any area bigger than 1.3 vitrinite reflectance, which is a maturity of the kerogen in the gas window. So we can conclude that this area has the possibility to be methane bearing. And then basalt. Basalt is a dark igneous rock with a fine grain texture and are composed of these plagioclase, pyroxene, micas, amphibole, and olefins minerals. And on this right side, this is a typical and generalized morphology of basalt lava flow, which consists of this chill-based, rubbly and vesicular basalt with a lot of vesicular holes or pores, overlain by this lower colonnade consists of these column normal joints as we can see here, and also entablature, which is this fanning columnar joints in basalt reservoir as the CO2 storage. Like for example, in the Wallula basalt in Washington State, they inject the CO2 into this lower colonnade because this section is the most porous and most permeable section in the basalt morphology. And this entablature is considered as the fluid barrier because they have the lowest permeability. Basalt is a very great candidate for rapid for CO2 storage because they have rapid mineralization reactions. It typically happens in like days to 1 or 2 years. So in Oklahoma, we know that we have basalt in these southern Oklahoma outcroppings, and we have the data, including 21 wells in terms of the cuttings and well logs. However, we do not know what kind of morphology we have in this Oklahoma, and currently we are investigating it. So let's talk a little bit about the OGS role. So this table shows that CCUS is a massive project, starting from these regional studies down to the long-term monitoring. And OGS has a position as a state agency as well as the official geological data repository in Oklahoma, has the capability to do most of these works in-house, including the geological and geophysical investigations. And to conclude this talk, I want to show this complex map again to show that we have a lot of sources where we can capture the CO2, and we also have a diverse and heterogeneous geologic formations where we can use to store the CO2 in Oklahoma. And definitely we have a strong experience to do the geological and geophysical investigation. Okay, I want to close this talk with showing you this short movie illustrating the potential carbon storage in Oklahoma. I think that's all. Thanks.